Hello friends, welcome back to Quantum Quandary. We'll be studying the properties of the delta function today. So the first thing that I wanted to look at is to more rigorously show that the following holds. So this should follow from this. Okay, that's what we want to show. And to just be completely mindful of everything that's going on, let's include the limits on this integral. So we're going to be looking at evaluating the following integral. The f of x is some arbitrary function, and we're going to evaluate it from minus infinity to x prime, okay? Oh, feeling a bit sleepy. So x prime is going to be the basically the variable that we keep, and x is the dummy variable that we're integrating over. A is some constant, it's real, that's all. Oh, excuse me. Okay, so we're looking at this. Well, what we want to do is we want to integrate by parts. So I'm going to use this as dv, and this is going to be my u. And, you know, I'm supposed to get uv minus v du. And let's just see what this integral is, this dv. So dx, we need the indefinite integral. dx of delta x minus a, well, we can use a substitution, remember? X minus a is equal to t. So we say dt of delta of t. We just remembered the substitution because we're big boys. And we get that this is equal to 1, right? No, it's not equal to 1. It's equal to the heaviside function. So let me just tell you why. It's equal to the heaviside function of t, which is the heaviside function of x minus a. Now the heaviside function is one which is 1 when x minus a is greater than or equal to 0, and 0 when x minus a is less than 0. So what we have is we have this delta function, right, of t. We're on the t-axis, and we're integrating, and if we stop our integration here, we get 0. If we stop our integration here or anywhere else, we get 1 from the integration. So this heaviside theta function or h function or whatever, it's either 1 or 0. It's 1 if we've gone over t equals 0, which is x equals a, and it's 0 if we haven't, okay? So just remember this one. Okay, so we've got our dv integrated into v. So let me just call this I. So I is equal to what we want, uv, right? That's f of x times theta of x minus a, evaluated from minus infinity to x prime, okay? And we've got minus the integral of v du, right? So that's dx theta of x minus a, and du is just df by dx, again from minus infinity to x prime. Now theta of minus infinity minus a is just theta of minus infinity, so this part is 0. We're going to include x prime, of course, because x prime could be anything. Theta of x prime minus a. And obviously, if x prime is less than a, we're going to have 0. But we'll leave that for later. And then here, this integral collapses into the interval from a to x prime because of this theta function, which is 0 when x is less than a. So that's dx, df by dx. But of course, this is just f, right? The integral of df is f. So that's f of x prime, theta of x prime minus a, minus f of x prime plus f of a. Now remember, we want to get f of a. Well, you know, we're not going to do any gymnastics here. We're going to show that f of a is the result. So that's f of a minus f of x prime, and I'm just going to factor everything, 1 minus theta of x prime minus a. So what we specified is that the integral from minus infinity to infinity of dx delta of x minus a f of x, the integral over the whole interval, right? That's equal to f of a. Well, the whole interval is just when we say that x prime is equal to infinity. Well, x prime equals to infinity gives us a theta of 1, and then this whole thing would be 0, right? So if we say that x prime is equal to infinity, or even to relax it a little more, x prime is just greater than a, then the integral is equal to f of a. And if it's not, if x prime is less than that, then we just get f of a minus f of x prime, whatever x prime is, which makes sense. There you go. So over the whole interval, the integral dx, well, I'm not going to write it again, but this holds over the whole interval. So if we know this, then we can also figure out the Fourier transform of the delta function. Just have a sip of water first. Refreshing. Okay, so we define the Fourier transform of a function f of x. That looks ugly. Like that. Of f of x as f tilde p equals minus infinity to infinity dx e to the minus ipx f of x. This is how we define a Fourier transform. And then to get f of x back, we need to integrate again, this time with a constant 1 over 2p for normalization of, well, let's do e to the ipx f tilde of p. Okay, so we can find the Fourier transform of delta x, and we can also express delta of x as an integral using these Fourier formula. So we then assume that the delta function also has its Fourier transform, right? Which I'm going to denote by this delta tilde of p. So you can notice these two are analogous. I mean, this specific one comes from the generic formula. And we're curious what this delta of p is. Well, delta tilde of p is minus infinity to infinity delta x dx. Let's use e to the ipx. Let's find it for delta of x minus a, okay? So for delta of x minus a, I guess we can put a little subscript a over here. Subscript a. And we know that this one is just going to collapse, right, into e to the ipa because of the property that we derived above. Which also means that delta 0 of p tilde is equal to 1, making the delta function a neutral element for this product and Fourier transform or for convolution. And now we can just express this delta of x as the integral from minus infinity to infinity dp over 2 pi e to the ipx. And in this case, we use this just times 1. So this is, I believe it's called the Cauchy formula for delta function, or someone's formula. In any case, this is a way to kind of write it as an integral. It's a nice sort of analytic formula for the delta function, as opposed to the sort of discrete distribution-y thing you get with the curly brackets. And if we wanted delta of x minus a, of course, all we need to do is include this e to the ipa. So e to the ip x minus a. I mean, this is a clear substitution, right? All you did here was say x equals x minus a. Or x goes to x minus a. Yeah. There you go. So it's the Fourier transform, and this little integration by parts. Hope you guys liked the video. Bye-bye.